Thank you for this opportunity. I'm going to talk about strong lens time delay estimation to share some useful statistical ideas with you. This is joint work with Casey Mandel, David Van Dyke, Vinay, Shelley, and Aneta. And this is my thesis chapter, actually. And this work was tentatively accepted with and also applied statistics. And this is the outline of today's talk. I'm going to first introduce, the main topic, the strong gravitational lensing. And I'll explain the data. And after I explain some assumptions of a model, I will introduce two estimation methods, Bayesian and frequentist methods. And then I will start talking about microlensing, which is the most common issue in time delay estimation problem. If I have some time, I want to introduce a new MCMC method for multi-modality, but I'm not sure. Are you all familiar with Metropolis algorithm? I know stat people. You? Okay. Yeah, then please give me some time to introduce in the end. Okay, let me first show you what strong gravitational lensing means. So you see images of two stars here, but actually these are from the same star. What happens is the strong gravitational field of this intervening galaxy behaves like a lens, splitting light into two images. Because the length of each path can be different, their arrival times can differ. We call this difference between their arrival times a time delay. So this is the image we see through the telescope. Oh, please jump into the talk whenever you find something unclear. Okay. This is another figure. This also describes the strong gravitational lens. Light rays are bent by this intervening strong gravitational lens. And because of this strong gravitational lens, we see multiple images of the same star in the sky.
So it's not just two images of the same star?
It be it is known to be up to 6, I think. That's the most recent article that I have read. So 2, 3, 4, 5, 6, kind of. So at each observation time, we measure the brightness of each gravitational lens images. So in this case, we may have 4 time series of brightness for 4 images. We use these data to infer the time delay. And the accurate time delay estimation is important because this time delay can be used to infer some cosmological parameters, including the Hubble constant that measures the current expansion rate of the universe. And this time delay can also be used to constrain some parameters in this equation of state of dark energy that tells us the expansion rate of the universe is increasing. It's not constant rate. So one thing I found interesting in this field is that this H0 means the null hypothesis for statisticians. But this means the Hubble constant for astrophysicists. So what do you do if you want to do some hypothesis tests on the null hypothesis? I mean the Hubble constant. Do you use different notation?
I don't know, actually. I've never encountered that.
Okay.
But yeah, I guess you have to come up with something like a script H. Maybe.
I see. Maybe null, maybe alphabet.
They make a lot of confidence intervals for the Hubble constant, but I guess there are different ways of measuring them.
I heard there are.
If they're equal in different measurement systems, so that would be a situation where you'd be doing hypothesis testing on Hubble.
Yeah, but never mind. In this talk, I will use H0 for Hubble constant. Okay, I prepare a simulated dataset for a doubly lensed quasar. A quasar is an active galactic nuclei. Its central black hole is actively accreting, like this. So the horizontal axis indicates the observation times, and the vertical axis represents magnitude, which is an astronomical measure of brightness. So at each observation time, we measure a pair of brightness of the two gravitationally lensed images of the same quasar. So if we measure these brightness over and over again, we obtain two time series of the brightness. And this data have 5 variables: the observation time, the observed magnitudes of 2 time series, and their standard deviation of measurement errors. Our job is to estimate the time delay, the shift in the horizontal axis between 2 time series. For example, this V-shaped valley appears earlier than the V-shape in the blue time series, meaning that the blue time series is lagging behind by about this amount of time. So my naive time delay estimate can be maybe 50 days, 50 to 60, because this is 200, 100, maybe 50. So getting a point estimate is simple. I mean, everyone can do that, naively. But quantifying the uncertainty of our time delay estimate is not simple. So we need a statistical model to quantify this uncertainty.
Are you certain that if there were no time delay, that the minimums would occur at the same time? Does the science dictate that? I know that for some other objects, like variable stars, if you look at things through, I guess these aren't different filters. These are just different sources.
This is from the same multi-filter. But because one arrives earlier than the other, there is natural delay between 2 brightness time series.
Okay, so the science says that the minimum should be at the same for the 2 if there were no time delay, but that the mean brightness could be different in the 2.
Yeah, because they pass different part of the gravitational length. Some is denser than the other, so some light rays are affected more by lensing magnification.
Okay.
So one can be brighter than the other because it might be passed through a denser area, or because lower magnitude means brighter objects. Is it clear? The goal is to estimate the shift between x-axis. So this is the model that I set up. Because the statistical model is a collection of assumptions, let me introduce my assumptions. The first assumption is that there exists unobserved underlying light curves that represent the true magnitudes in continuous time. So these red and blue dashed curves are these true continuous time curve that we don't observe. Let me use this capital X of t, time t, and capital Y of t to denote n true magnitudes evaluated at n observation times. So these are values on the curves evaluated at n observation times. So you can think about capital X of t as a function of observation time. This assumption says that, means that our observed magnitudes are generated by true magnitudes up to some measurement errors. So with some measurement errors, which is denoted by half length of vertical line, there are true magnitudes. Our second assumption is the most important assumption. Our second assumption is that one of the latent light curves is a shifted version of the other in horizontal axis by the time delay. and by beta naught in the vertical axis. This assumption is called a curve shifting assumption, because if we moved red curve by time delay to the right and by beta naught downward, then two latent curves would exactly overlap. Questions? Okay, the third assumption is that the observed data follow Gaussian distributions centered at the true magnitude. For example, here y, small y, is a realization of this Gaussian distribution centered at the true magnitude. And the standard deviation of this Gaussian distribution is the standard deviation of measurement errors. And based on the curve shifting assumption, we can replace this capital Y with a shifted version of capital X. And by doing this, we can have the time delay as a parameter of a Gaussian probability distribution. So this is how we can quantify the time delay using a statistical model. Okay, here I just replaced the capital Y with a shifted version of capital X. So based on this assumption, the probability density function of the observed data is a product of independent Gaussian density functions. So this is Gaussian density function, and the second one is also independent Gaussian distribution. Oh, let me use the notation. Let me use t to the delta to denote a vector of length 2n for sorted observation times. So t is the vector of n observation times, and t minus delta is a shifted observation times. And I sort these times to make it in the order of increasing order. The first assumption is about the latent data. I assume that the latent data follow an Ornstein-Uhlenbeck process, which is also called damped random walk process among astrophysicists. This is because many astrophysicists have empirically shown that this Ornstein-Uhlenbeck process describes the stochastic variability of the quasar light curves very well. I think this research has begun since Brandon Kelly introduced the seminal paper about the application of Ornstein-Uhlenbeck process in 2009. This Ornstein-Uhlenbeck process is based on this stochastic differential equation. Tau is the mean reversion time, which is also called characterization time among astrophysicists. And when the process deviates from the overall mean of the process, this tau represents the time for the process to come back to the overall mean. So if the process deviates from the overall mean, this tau is the length of this time for the process to come back to the overall mean. And mu is the overall mean. Sigma is the short-term variability of this process. Capital B of t is a Brownian motion. So the difference between Brownian motions follows Gaussian distribution. You can think of this Ornstein-Uhlenbeck process as a Gaussian process with a Mattern kernel 0.5 parameter. So by assuming these latent magnitudes have some Gaussian distribution, the effect is, Gaussian process is a continuous time process, something like this. By assuming these latent data follow a Gaussian process, we can say if we evaluate this Gaussian process at discrete observation time, then these three values for example, xt1, xt2, and xt3 jointly follow a multivariate Gaussian distribution. This is the effect of assuming Gaussian process for latent data. So simply, this probability density function of the latent data, latent magnitudes, is just a product of Gaussian marginal times Gaussian conditionals, because we are assuming they are jointly following multivariate Gaussian distribution. Okay, I want to talk about how we set up prior distributions in detail, because it can be used for your research, I think. So from statistician point of view, using an improper prior distribution is convenient, because improper prior distributions are well known and non-informative. For example, people usually use improper flat uniform prior distribution on regression coefficients. But if we use improper prior distributions, we must check whether the resulting posterior distribution is proper or not. I mean, we need to check whether this integration over posterior distribution is finite. Without knowing this, even if a Gibbs sampler gives you some result, some well-shaped posterior sample, we can't say whether that sample is coming from our target posterior distribution. So this is well-known fact published in 1994. So in my model, proving this finite integral is very complicated, because likelihood is so complicated function of parameters. So to avoid that trouble, we decide to use all proper prior distributions. Then from astrophysicist's point of view, then how we set up proper prior distributions? I mean, the constants in the prior distributions. For example, this is the whole prior distributions in our model. So for the time delay, we use a uniform distribution. And the range of this uniform distribution is determined by two cases. If we know some prior informations that can constrain the time delay a priori, for example, if we know some physical model of lens and gravitational potential of the mass and gravitational potential of the lens, rad shape, and the relative location of the quasar and the lens, we can constrain the range of the time delay. If we don't know that information, that is usual in many cases, we use this specific range. We call this range the entire range, because the time delay outside that range looks like this. There is no overlap between two light curves. So that range restrict shifting the light curves in this way. This is the left margin of that range, and this is the right edge of that range. So within this range, there is at least one data point overlapping between two light curves. We set up another uniform distribution for the mean of the OU process, the underlying process, between -30 and 30. This is because the magnitude of the sun is -26.74, and the faintest object that Hubble Space Telescope can identify is 30. So practically, most brightness measure is between this range. And because beta naught is the difference between two magnitudes, we can just double the range, because we know that the difference between two magnitudes can't be outside this range. And this is something that I want to share. When it comes to set up a proper prior distribution for the parameter, positive parameters defined on positive real line, for example, variance and time scale, we decided to use inverse gamma distribution. People usually use inverse gamma distribution for the unknown variance component because inverse gamma distribution is a conjugate prior distribution, which is convenient. But actually, inverse gamma distribution has more meaning than that, just conjugacy. Suppose this random variable x follows inverse gamma AB distribution. And the probability density function looks like this. And the mode of distribution is b over a plus 1. I'm saying this assumption sets a sub-lower bound of a random variable. Here I displayed an inverse gamma distribution 1 and 1. And let's think about this. What would happen if x goes to infinity? If x goes to infinity, this part goes to 1. And this part only determines the tail behavior, meaning that if x goes to infinity, the probability density function decreases to 0 with a power law, just determined by this power. On the other hand, if x goes to 0, the density exponentially decreases to 0 because this term dominates. So for this random variable, it is very difficult to have a value smaller than the mode, because it exponentially cuts up the likelihood of that possibility, the possibility. So keeping that in mind, let's think about why we need to set up a sub-lower bound for each of these parameters. Okay, why do we need a sub-lower bound for the scale, for the short-term variability of the OU process, the underlying light curve? Let's think about this. Suppose this is OU process, latent light curve. What would happen if this variability is much smaller than observation measurement error? So the setting is, this is the sigma, and your measurement error is like this, huge. In this setting, how would the data look like if you find the observation? Would the data reflect on the fluctuation of the underlying process? For example, this time you observe here because you measure the observation within measurement error. So it can be here, it can be here. I mean, by chance, it can be here. It would be a white noise. The observed data wouldn't reflect on your underlying fluctuation because the underlying variability is much shorter than the measurement error. So we have motivation to set up a sub-lower bound for this parameter. Let's think about tau. Tau is the length of the OU process, I mean, time scale of the OU process. The situation is, this time is like this. Suppose this is the underlying process. What would happen if our observation cadence is much larger than than tau? For example, in observation cadence, much larger. What would happen? what would the data look like? So, for example, you are observing here, you are observing here. I mean, it goes this way. You are observing here.
Where is tau in the kernel again?
Okay. Tau determines the scale of the OU process. So it affects how much deviations can affect the overall process, I think. Even if this is 0.5, if this is very small, that difference will be huge.
You mean in your data, your measurement error is very huge?
Oh, this is the separate story. We ended this. Our second scenario is this. Suppose this is underlying OU process, but your observation time is here, here, here. So you will observe some, suppose measurement error is appropriate like this, it's much smaller. So you observe here, and you observe here, you observe here. So this information may not tell you anything about this observation because the fluctuation is already much shorter than your observation cadence. So they will be uncorrelated, but because we are assuming Gaussian process, they follow multivariate Gaussian distribution, meaning that they are independent. So your observation, again, will be white noise. So we have another motivation to set up a lower bound of this random variable. Oh, the time scale. So let's think about how we determine the constants in the inverse gamma distribution. So we provide two ways to set up this constant C. In this case, slope lower bound would be C over 2 based on this formula. The first way is to set up C equal to typical measurement error, so that the slope lower bound is half of typical measurement error. So in this case, the C is dependent on each data. So we refer to this paper, Liu et al. In 2010. They analyzed 9,275 quasi-Lie curves using the OU process. And we confirmed that that number is smaller than the minimum of the all 9,000 estimates for sigma squared. So our lower bound will be automatically smaller than at least these number of estimates. So we are trying to put the true value of the sigma to the right side of the slope lower bound.
If you make like a histogram or something of the tau found by plot, does that look something like this? You sort of want your prior to be whatever values they were getting.
As far as I remember, their histogram of estimates is skewed a little bit.
Okay.
So this x-axis will be sigma squared. And this is density. So we are setting our C equal to, this number is actually about here. So our slope lower bound will be smaller than, just half of this number.
But it doesn't make sense to just estimate the parameters in the inverse gamma from histograms or from?
This is independent research from this. So prior information comes from some independent source of this research. So we are not using data.
you're using the data to just find this lower bound.
This is not data, actually. I mean, these are estimates based on that data. These 9,000 data. So these 9,000 data can be considered as previous studies.
Yeah, I guess it's not that I'm saying that you're using your data in your prior, and that's a problem. I'm not saying that. What I'm just suggesting or curious about is you could use that previous data just to and fit the two parameters in the prior to that data.
We can use that. That is kind of empirical based approach.
And this is just an alternative to doing that?
Yeah, we choose this prior so that it can be used for any quasi-liker. That's the idea, but 9,000 might not be enough to tell robust choice for the C. But as long as C is small, you can put the truth to the right of the mode. So smaller would be better, but this soft lower bound prevents extremely small tau, because if tau is extremely small, we expect to observe white noise. So this is our way to set up prior distributions. Any questions here?
And why not Cauchy prior?
Because
Cauchy prior also has, or you need a soft.
This is positive random variable, so Cauchy is defined on real line. Is it your question?
Sometimes people use half Cauchy for priors, but I guess you don't have the conjugacy to Cauchy, right?
The reason, so Cauchy is defined on real line, but these parameters are defined on positive. So
I remember they use the log sigma, so for the.
log sigma. I mean, yeah, that's one
And
possibility.
if you use Cauchy, then there is no peak like this. Like here, you have to shoot the peak from 0 to 5 from 0.
Yeah, I think if you use Cauchy, there is no exponentially decreasing part. It's just exponentially increasing. Power law. Power, yeah. I forgot to mention this. So, any more questions? So, in this case, our soft lower bound is 0.5 day for the time scale. So, at least our team members think this 0.5 day is reasonable soft lower bound, because when we observe the light, we can't observe the light during the day. So our observation cadence will be at least 1 day, kind of. And also we confirmed that this 0.5 day is smaller than 9,000 estimates of tau. So this is our way to justify, but I'm pretty sure there might be a better way to justify our choice prior. Okay, based on the prior distribution, we can derive the full posterior. Let me use theta sub OU to denote the parameters in the OU process: mean, short-term variance, and time scale. And the full posterior density is proportional to a multivariate Gaussian density of the observed data and multivariate Gaussian density of the latent data, and the prior density functions that we just set up. Given this full posterior, it is not difficult to derive a Gibbs sampler. In our case, we update the true magnitudes and time delay together, and given these, we update the magnitude shift offset. And given this, we update the OE process. But I think Bayesian method has its own pros and cons. Like for example, Bayesian method provides a complete summary of all the model parameters, including the entire joint distribution. I mean, that tells us the relationship between parameters. But Bayesian method can be inefficient if some parameters have multimodal behavior, multimodal distributions. So that's why we need something else. That's why we came up with using profile likelihood. A profile likelihood is one way to integrate out the model parameters that we are not interested in. So the likelihood function is defined as this. Likelihood function is the integration of a multivariate Gaussian distribution times another multivariate Gaussian distribution. And the integration is over the true magnitudes. So the result of this integration depends on the value of parameters and the data. Because data are fixed, we can think about this integration as a function of all the model parameters. And profile likelihood is maximized likelihood with respect to the model parameters that we are not interested in, which is called nuisance parameters. And in the manuscript, in the paper, we have shown that this profile likelihood is asymptotically proportional to the marginal posterior distribution of the time delay. This is our goal to estimate, right?
Is this Berger?
We use that. We refer to that paper.
But is this Duke Jim Berger or
That yeah
J.O.
no. Are they different? I thought J.O. Berger is at Duke.
Okay, maybe J.O. Berger is at Duke. There is another Berger, and I'm wondering if it's that one or.
No, I think Berger at Duke.
Oh.
Yeah. Okay. Yeah. Using this profile likelihood, we can calculate this approximate posterior mean, standard deviation, and in particular, we can learn the shape of the distribution by drawing a profile likelihood curve. However, this profile likelihood has its own pros and cons. This profile likelihood is simple to calculate because profile likelihood is a function of a single parameter. So you can just draw a line over the space of the time delay. By drawing a profile likelihood curve, we can check multimodal behavior of the time delay before we run any Bayesian methods. But drawing a final curve can be computationally expensive because we need to evaluate profile likelihood on a final grid of values of the time delay if you want a final curve. But nowadays, because we can parallelize computer sources, I think it may not be a problem. But the real problem is this profile likelihood curve doesn't tell us anything about the relationship between parameters. Question?
Won't this also be like, I mean, if you just think maximum likelihood, like we all learned in our first year, right? So doesn't having to estimate this beta naught and theta hat, isn't that going to bias your estimate of delta that comes out of this profile likelihood?
That's a good question. So here, if we maximize this profile likelihood,
yeah.
then these are all the maximum likelihood estimates.
Right. No, I understand. But
So at each value of time delay, you can also get the maximizing value of the other parameters.
Yeah, no, I understand that. I guess what I'm asking, so in your super simple case, right, if you think back to IIG normals in the very beginning of statistics, you find that the estimator for sigma hat or sigma square hat is biased, right? The maximum likelihood estimate is biased. And that's why we don't use that one, right?
Yes.
So the maximum likelihood estimate is biased because you have to estimate mu using x bar.
Yes.
Yeah, right? So that's what that phenomenon is what I'm asking about.
Oh.
The fact that you have to estimate these parameters is going to, it may only be by a little bit, but won't it also, I mean, that's why you do Remel likelihood, right? To get out of that problem. So how does that affect these estimates?
That's a good question. In Remel estimate, they use integrated likelihood. They try to account for the uncertainty of the Nuygens parameters. So
well,
they are used.
Usually you multiply by some error, you basically multiply by some error contrast or transform to error contrast so that there is no mean to be estimated. So basically you get rid of the Newton's parameters.
I think that is integrating out, and the constant is the constant of the Laplace approximation thing.
Okay, maybe we're saying the same thing. Continue.
Oh, we can talk later.
Okay.
So we use this profile likelihood as an approximation to the posterior to guide our Bayesian method. So even if it is a little biased, we run our Bayesian method based on this information. So I will talk about that. So our team thinks that Bayesian and frequentist methods are complementing each other, because Bayesian method is inefficient when there exists multimodality, but profile likelihood doesn't care about the other model parameters, so that we can check multimodal behavior. So our time delay estimation strategy mixes these two methods. We first obtain the entire profile likelihood curve and check the multimodal behavior. And we initialize our Bayesian method near the mode to finalize our estimate and to study the relationship between parameters. So our final inference will be Bayesian estimates. We use profile likelihood to guide our Bayesian method. Because in this case, we can avoid the multimodal issues of our Bayesian computation. So let me introduce time delay challenge. Time delay challenge is a blind competition held by 8 astrophysicists from 2013 to 2014. The goal was to provide an observational strategy for the largest synoptic survey telescope. Because we can say, based on the result of this blind competition, they can say, okay, it would be better to visit a specific part of the sky maybe by 3 days that optimize the time delay estimation. So the second goal was to improve the current time delay estimation methods in preparation for the era of the Large Synoptic Survey Telescope. So the organizers generated 5,000 simulated data sets, and 13 teams blindly analyzed these 5,000 data sets using their own methods.
So one data set is one time series or one pair?
So 5,000 pairs of light curves, you can think of that. So we need to estimate about 5,000 time delay estimates. So this is the result. This is the result of the last stage. And our team is denoted by baby blue triangle here. And F indicates the proportion of data sets we analyzed. This means that we just analyze 20% of 5,000 data sets. And P is the precision. Precision is, you can think about uncertainty quantification. And A denotes accuracy. In statistics, I interpret this A as bias. And chi-square is a squared, standardized residuals. So with respect to F, we analyze second largest number of data sets.
Did you not analyze them all just because computationally it's hard, or
I will talk about that. Because there are a lot of issues that prevented us from analyzing data set. So successful estimates were just 20%, maybe about 30% of all the data set. And our precision was the best, and our accuracy, which is near 0. So this is one of the best. Oh, by the way, the gray areas are what the organizers aimed at. So they expected the results would be in the box. And our chi-square is like in the middle. It's kind of mediocre performance. Then why? Why we got the best precision, best accuracy, but mediocre chi-square?
You want large precision?
Precision? Precision would be better if this is smaller, because this is low scale. And so if precision is close to this, or we can think about this.
So what is precision?
Precision is,
Is that not inverse variance?
precision is our uncertainty quantification, uncertainty of time delay over true time delay. And there are 5,000, right?
Oh, okay.
They are averaging over this. So this is coefficient of variance in statistics.
Okay.
Mean of that coefficient of variation.
So small is good.
Yeah, small is good. Small is good. So this is one of the simulated data sets in the time delay challenge. This is a doubly lensed quasar. And our analysis routine is to obtain the profile log likelihood of the entire space of the time delay. And then we exponentiated it. We found a dominating mode of the space. So we initialized our Bayesian method near this mode. I magnify the dominating mode of the profile likelihood here, and I display the posterior sample of the time delay on the right panel. The red vertical line indicates the true time delay. It seems like our model catches the true time delay within some range, within some uncertainty range. So I numerically summarize our estimate. So it seems like it's about 1.5 posterior, within the 1.5 posterior standard deviation. And during the competition, we didn't know the truth, so we tried to check our estimates. So here, we shifted the blue time series by our estimates, shifting x-axis by our time delay estimate and vertical axis by our beta knot estimate. Seems like the fluctuation patterns are almost identical.
Why sometimes you only have blue and no red?
Oh, here?
Yeah.
Because I shifted by our time delay estimate.
Oh.
I shifted by our time delay estimate, and then I moved the curve upward by our time delay, beta knot estimate. And we also check our model by doing some posterior predictive check. And these gray areas represent our posterior prediction for the observed data. So since gray area encompass the data, we can say our model is reasonably explaining the observed data. So this is what we did. But do you remember we did some bad performance in chi-square? And this is why. So microlensing is a common problem in time delay estimation. And this effect occurs when stars unusually close to our line of sight, introduce some independent noise into lensing magnification. In other words, based on my understanding, the stars near the path of light behaves like another small lens, affecting lensing magnification. So in this case, the observed data exhibit two sources of variation. The first one is intrinsic variability of the quasar, and the second one is independent extrinsic variability. And usually this extrinsic variability appears as some different long-term trends, for example, polynomial. In this data set, you see they seem to have different linear trends, although their intrinsic short-term variabilities are very similar. So the problem is, if the data suffer from microlensing, our curve shifting model doesn't work well because one of the latent light curves is no longer a shifted version of the other because they have different long-term trends. It's not exact matching. So I just tried running our profile likelihood curve on the data set with microlensing. So here, a vertical red line indicates the true time delay. But our profile likelihood at this true time delay is very small. It gives us some large modes on the margins. I tried to check these three time delay values using in these three plots. So in this plot, I shifted the blue time series by the true time delay. So this is, but the fluctuation patterns don't match regardless of shift in y-axis because they have different trends. So if there are different trends in two light curves, the two light curves match up with a small overlap at the edges of two light curves. So by chance, they look like very well connected because at the tip of each light curve, it is possible to find some matching point. They look like very well connected. So this model thinks that, okay, these values are very more likely than the true time delay. So we can also think of these spurious modes as evidence of model misspecification. We are using we are analyzing the data with microlensing with a model that doesn't have microlensing adjustment. So this is why we perform bad in time delay challenging, because most of data sets suffer from this microlensing. So after the competition, we developed a model to explain this microlensing effect. People usually use polynomial regression to remove the long-term trends. So, but our way is a little different. We fit a polynomial regression on the difference between y and x. So y minus x has polynomial regression. So you can think about this. These lines are what people try to remove. But what we are removing is the difference between the long-term trends. In other words, this equation tells us that we need to think about this red time series as a tilted x-axis. So this is our tilted x-axis, and on this tilted x-axis, we are fitting a linear regression on blue time series. What happens is the regression removes the trend, and it moves down the blue time series to the red time series. Although the slope is not 0, but still we have chance to match the fluctuation patterns because they have the same long-term trends. So the effect of this is we can reduce the number of parameters. Because what people do is fitting a linear regression. I mean, they need 4 parameters, slope, intercept, but we just need slope, intercept on this tilted x-axis to remove the trend.
But you have to solve for that at the same time as solving for delta. You have to estimate the coefficients in the polynomial.
Oh, yeah. I mean, within Gibbs sample, it is iterate. I mean, at each iteration, we estimate beta, time delay, the other multi-parameters, and we repeat this estimation process, sampling process.
So, but if you do the polynomial regression separately for each time series, then you can do that first, subtract off those differences, and then you don't have to do that regression within the.
Yes, exactly. But in that case,
You have more parameters there. And
in that case, we can't account for the uncertainty
yeah.
within the estimating regression coefficient. So it is I think it is desirable to incorporate this polynomial regression into your model.
Yeah.
This is how it works. But people usually remove the trends, and then they use their own method without accounting for the trends difference.
You can use that to like initialize your sampler, like the crude thing.
Yes. Yeah, that can be our crude estimate. I mean, initial values of our MCMC. So we use a cubic polynomial regression as a default because some astrophysicists successfully accounted for microlensing effect in 3 different systems. So using this cubic regression adjustment, we run a profile log likelihood, and then we exponentiated it. Here, the spurious mode on the margins disappeared. So this time, there is just one dominating mode. So we initialize our Bayesian method near this mode. And the same thing, posteriorly distribute sample of the time delay, and I superimpose the profile likelihood curve. And this is the truth, but it seems like truth is, our distribution is off the truth a little bit. So I numerically summarize our estimate. It seems like our model catches the truth within 2 posterior standard deviation. Because chi is the difference between our estimate and truth over our standard deviation. So we also check our estimates and our model using gray areas, the posterior prediction. It seems like fluctuation patterns are very similar. So we report our estimate with sure.
So for the plot on the left here, it's kind of
this
like
one?
it's almost periodic with
This one?
yeah, and then there's kind of a maximum value. So is that when you're doing a shift and the points don't line up at all, and you reach some maximum for the log?
When you shift and when you adjust the microlensing, if this is very likely, then it gives a peak. But there is a huge gap. If we shift our blue time series within this gap, there is no matching observations.
Okay.
So that's why we have some almost uniform mounds here. But once it starts overlapping, maybe some of them overlap overlap. Some of them overlap, but the others are not. So that's why likelihood goes down.
Okay, so you don't really have much information when there's no overlap, so there's a decent
Yes.
likelihood. But then when you get bad overlaps, it goes
Then
down.
it determines whether it is okay or not. So it's kind of finding the likelihood for the well-connected fluctuation patterns. This is the second example. I prepared two realistic examples. One is about quasar Q0957 plus 561. I don't know why they always have telephone number like this, but they use that. So this quasar is the first gravitationally lensed system discovered in 1979. Since then, we have monitored this quasar. And we use the most recent, at the time, the most recent 3-year-long time series data observed at US Naval Observatory. And we conducted our estimation routine here. And we also checked our estimate and model. There's actually one thing very interesting. Our estimates are reasonably consistent to historical estimates, although we use the smallest number of observations. The reason is maybe partially because our data were measured most accurately, compared to other measurement errors. The real interesting thing is here. I denoted the historical estimates by vertical dashed lines. So it seems like some estimates are near the second highest mode, and only two of them are near the highest mode. So I think in in summarizing multimodal distributions, just two numbers, mean and estimate, is not enough. Because two numbers, the estimate and uncertainty of that estimate, is valid for unimodal distribution. Especially when that estimate has some Gaussian distribution. That is the underlying assumption. So in this multimodal case, showing the entire distribution is the most informative way to summarize the result. Because otherwise, one day, you will find your estimate is, you may not know whether your estimate is near the second highest mode or the highest mode. Actually, this is the most interesting example to me. So this example is about quasar J1029 plus 2623. This quasar is known to have the second largest time delay, about 2 years. This is the data reported in this paper, and we conducted our estimation routine to obtain posterior distribution of the time delay with profile likelihood superimposed. And we also checked our model and our estimate. Our model checking is based on gray area, and our estimate check is based on the shift of blue time series. So the most interesting thing is this. So we are all using the same data set. Then we should have something similar, regardless of methods to be used, right? But the point is, our estimates are lower than the historical estimates by about 10 days. This is not, I was very surprised at the time. And also, our 90% interval estimates are much shorter than their estimates. This is about 20 days, but this is about 4.5 days. This is huge difference. Based on the same data set, I was very surprised. But at first, I was very happy because I thought, okay, our method gave us the most, our method constrained the uncertainty the most, compared to others. But actually, I was wrong. The first thing I needed to think about was whether our model was overconfident, whether our model was not well calibrated, because our interval estimate is much shorter than the others. Do you have any ideas about what's wrong here?
Do some measurements have very small photometric errors?
But we are using the same data set. So this is the answer. So I displayed posterior sample of the time delay obtained under different microlensing order. So here I don't use microlensing adjustment. Here I use linear trend. Here I use quadratic trend. Here I use cubic trend. And I display their estimates by vertical dashed line. And the arrow on the top indicate their 90% confidence interval. So let me describe their methods. The four Mr. et al. Use a point estimator based on high-dimensional optimization. And they choose the order of microlensing adjustment by statistical information criteria. Their AIC chooses a linear adjustment for the microlensing, and their BIC gives them a model without microlensing. And in a mysterious way, they averaged over the results of these two estimates. Kumar et al., they also used a point estimator based on high-dimensional optimization. This is actually chi-square minimization, if we are familiar with. And in terms of microlensing adjustment, they use a spline with a Gaussian kernel. But the point is, it seems like their optimizer got trapped in a local mode. But their confidence intervals are almost covering every mode that I found. It seems like, okay, they use a bootstrapping. They call Monte Carlo simulation. But in statistical term, that Monte Carlo simulation in astrophysics means a parametric bootstrapping. So they found this point estimator and generate a lot of data set and estimate the time delay, and they got this interval. That means they found also multimodal behavior of the time delay. Otherwise, they couldn't get this wide confidence interval that covers almost all the possibility. So if we increase the microlensing order, then multimodality almost disappears. And this is why our estimate is much smaller than theirs, and our interval estimate was much smaller than theirs. So our conclusion in the paper was that, okay, they might not account for the microlensing enough in an appropriate way based on these evidence.
With the microlensing is accounted for by the cubic?
Yeah, the polynomial regression. Our next step is to take part in the second time delay challenge. This time, the organizers will be more realistic. Previously, they just provided a pair of light curves for one time delay. For each time delay, there were a pair of light curves. But this time, they will provide 6 pairs of light curves per time delay. These multicolor light curves are based on 6 different optical bands, U, G, R, I, Z, Y. And they will generate more than 5,000 systems. And each system has 6 band data. And each band will be composed of 150 observations. So this is actually a huge data set. And they will also simulate in this way, simulate the data in this way. The blue filters will be more sensitive to microlensing effect, meaning that bluer light curves will have more extrinsic variabilities, independent of intrinsic variability. And all the information will be given to calculate the Hubble constant. That means if we have 5,000 time delay estimates and there are uncertainties, it is automatic to have the Hubble constant based on basic cosmology, like lambda CDM. So the evaluation will be based on two numbers, our Hubble constant estimate and its uncertainty. So if you are interested, you can visit this website. And if you, I actually prepare maybe for 20 minutes. Would it be fine? I prepare another topic for a Markov chain Monte Carlo method for multi-modality. OK. If you're familiar with Metropolis algorithm, I think it'd be fine.
I did have one question on the
question.
this talk. So if you just talked about where you have two on the images, so you get images and then you have two objects that are separated. If they are further apart on the images, does that suggest that there might be a longer time delay than if they're right?
Yes.
Okay, but nobody's incorporating that information.
I mean, if we have the information about the mass of the lens, how big the lens, then we can constrain the time delay, the range of the time delay.
Okay.
Yeah. If we have the information about mass of the lens and the location of the lens and quasar and redshift, then we can reasonably constrain some range. I mean, it can be larger if they're farther apart. The reason I introduced this is that this method came from the time delay estimation project. But we couldn't use this method because we solved the multi-modality by scientific knowledge about microlensing. I mean, once we knew the microlensing, the multi-modality disappeared, so we couldn't use this method. But this method was developed based on the time delay estimation problem. We actually call this, at first, we named this algorithm as a repulsive attractive metropolis. But David said, oh, that's a little negative, because people may remember our algorithm as something repulsive. So we changed its name to repelling attracting metropolis. And after changing its name, we realized that the second meaning of repelling was repulsive again. So we decided to call this algorithm a RAM. Yeah, a RAM. For UNC people, it's good. Yeah. So this is about the time delay estimation problem, the posterior distribution of time delay and the other model parameters. So we use a Gibbs sampler, as I told you. And the conditional posterior distribution of the time delay is not available in a closed form, meaning that we use a metropolis algorithm to update the time delay within the Gibbs sampler. So this algorithm is called metropolis within Gibbs sampler. And here I displayed 1 million posterior samples of the time delay. So seems like there are two distant modes, and let me tell you about the distance. So the local posterior standard deviation of this mode is about 1.2, 1.5. And the posterior standard deviation of these modes is 25 days. And the distance between these two will be about 700. So these are far from each other. Because of that, our metropolis algorithm rarely jumps between these two regions. So there were just 8 jumps out of 1 million iterations. So if our MCMC method doesn't jump between modes frequently, then the estimate of the relative height of each mode is not reliable. Because it is possible that our method couldn't get out of these local modes. I mean, just because of that, not because the relative height of the modes are exactly this. So our question was, could we improve our metropolis algorithm to explore multimodal distribution in a better way without losing simplicity of the metropolis algorithm? I mean, there are potentially a lot of tempering methods, but the learning curve of the tempering methods is huge because there are so many tuning parameters you need to adjust. So here is the idea. Suppose there is a ram on the top of the mountain. How would this ram move to the top of the other mountain? Any ideas?
Iron Man.
Oh yeah, that's true. Because this is animal, these are not available actually. So our idea was, okay, in order to move, let's go down first and then go up. So let's make a downward movement in density to generate a proposal. Let's go down first to the valley and then go up, like a real ram does. And then let's determine whether we accept or not this proposal using this metropolis Hastings ratio. This is the ratio of target and the ratio of proposal density. Let me use Q to the du to denote a downward proposal density function. So this is the key idea of this algorithm. There are so many ways to make a downward movement in density, but we use this two-step procedure. We first generate an intermediate proposal going down, and given this intermediate proposal, we are generating a final proposal going outward. Specifically for the downhill move, we use a metropolis algorithm, generating a proposal from Gaussian distribution given the current state. But if you know metropolis algorithm, you know that the target density of the proposal appears in the numerator. But we flipped. So this reciprocal ratio prefers lower density state because in this case, lower density state has a higher chance to be accepted. For example, suppose this intermediate proposal decreases the density, the target density. Then this part is smaller than the numerator. So the acceptance probability will be 1. And if any proposal decreasing the density will be accepted for our intermediate metropolis algorithm. And here's the sigma, the proposal scale of this proposal distribution, is our tuning parameter, like a metropolis algorithm. The same tuning parameter to metropolis algorithm. And we add a small constant to the numerator and denominator to prevent a ratio of zeros. And we repeat this step, generating a downhill proposal until 1 is accepted. We call this a forced metropolis because we force the current state to move somewhere until we accept something, until it moves. And given this intermediate proposal, we generate a final proposal using another Metropolis algorithm, flipping back the ratio. So this original Metropolis ratio prefers upward movement, as you know. And we also repeat this step until one proposal is accepted. But in order to run this algorithm, we need to calculate the acceptance probability because, okay, we generated a proposal making a downward movement. But the problem is, this acceptance probability, the Metropolis-Hastings ratio, contains an intractable integral within the acceptance probability. So we can't calculate the acceptance probability, and we can't run our algorithm. So the question at that time was, can we avoid this, calculating this integral, the ratio of integrals? And the answer was, if we explore an extended space by introducing another auxiliary variable, then there is a possibility to cancel out this ratio. So this is what I did. I introduced another random variable, z, that shares the same space with x. So you can think about z as copy of x. And in the extended space, the joint proposal density function can be factored into marginal times conditional. This is based on probability theory. And our assumption is that the conditional target distribution is Gaussian. And in the expanded space, the joint proposal density can also factor into these two conditional distributions. The first equation is based on probability theory, and our assumption in the second equation is that the first conditional distribution is a downward movement, downward proposal density function. And the second conditional distribution is a forced downhill kernel density, meaning that to generate a joint proposal, we first generate a proposal of x double prime by making a downward movement. And given this x double prime, we generate an auxiliary variable going downward. So based on these assumptions, the joint acceptance probability, which is a ratio of joint target density times a ratio of joint proposal density, becomes free of any integrals that we encountered. So now we can run this RAM algorithm. So RAM algorithm has 4 steps in each iteration. The first 3 steps generate a proposal. And the last step determines whether we accept this joint proposal or not. For example, in the first step, we are generating an intermediate proposal going downward. And given this intermediate proposal, we are generating an upward proposal. And given this final x double prime, we generate a downhill auxiliary variable. And then this final acceptance probability is easy to calculate. There's nothing intractable. So the idea is, okay, if there are multi-modes, let's go down first and try to find some area where density increases. If there are multi-modes, let's go down. And if we try to find the area where density increases, it can be the original mode or the other mode.
Is there any issue that you're going to keep going back into the same mode that you were
That's a
in?
good question.
I can imagine if you have 2 modes, a lot of times the density is going to be decreasing for a long time, and there's some exponential tail, and then it's going to go up. So
Yeah, there are possibility that it goes up. It goes back to the original mode in that case. In many cases, it's not. It's not. Yeah, it's about 70%. It depends on the surface of the multi-modes. But in extreme case, it was about 70%.
If you were finding that was happening, though, couldn't you just adjust your metropolis standard deviation, make it bigger so that your step is bigger?
We will handle that.
Farther away from the
Yes.
original mode?
We will handle that. Yes.
And it's still stationary?
Oh, yeah. That's a good question. So this is a metropolis Hastings ratio. This is the ratio of target times the ratio of proposals. If you believe a metropolis Hastings algorithm preserves the target distribution, RAM also preserves the target because this is metropolis Hastings ratio with different proposal density. Usually it is something Gaussian, but our proposal density is a little bit more complicated, but still within the framework of metropolis Hastings. Question?
How does this work sort of with your forced metropolis step? So,
That's a really good question.
well, like computation time.
Yes, that's a really good question. And usually, I will compare the computation time with metropolis, just simple.
Yeah.
How much?
That's painful enough.
It's not. It's about 4 times on average if you run a million iterations.
This downhill, uphill.
Usually downhill is immediate because there can be so
But to find
large.
it going
Yeah,
back
it
up.
usually takes 2 to 3 iterations
Okay,
on
so
average.
Overall, it takes 4 times.
4
as long
times
for
slower.
regular metropolis.
4 times slower than metropolis Hastings.
Okay.
But we account for the CPU time, so example will be interesting. So let's see how this RAM works in time-delay estimation problem. So we use a Gibbs sampler, and we update the time delay, and given this time delay, we update the other model parameters. And we use temper transitions and metropolis or RAM algorithm to draw the time delay in the first step. And this, let me explain the configurations. So we run 10 chains, spreading 10 initial values across the space of the time delay. And actually, this tuning is based on metropolis, because we just replaced metropolis with RAM with the same proposal scale. So we set up scale 500, considering the best performance of metropolis algorithm. And 500 is huge, considering the range of search space. We consider 2 scenarios. We run 3 algorithms for the same number of iterations. And in second scenario, we run 3 algorithms for the same amount of CPU time for a fair comparison. So this is a result of running algorithms for the same number of iterations. So temper transition spends a lot of CPU time. And it bridges, OK, let me explain this. So this is the number of chains that jump between these 2 regions out of 10 chains. And this is the total number of jumps between these 2 modes. So there was just 1 chain jumped, and that chain made 4 jumps between modes for metropolis algorithm. So metropolis algorithm is the fastest because we know that this is the simplest algorithm. We can just increase the scale. That is the simplest solution to handle multimodality, right? But actually, within these 100,000 iterations, just 1 chain jumped. Because metropolis algorithm is known to be inappropriate in multimodal situation. But let's think about this. RAM and temper transitions are making similar number of jumps, similar number of chains. But the relative height of the modes near 400 is different. So we interpret this result as something like, OK, this is evidence that the Markov chain hasn't converged to the target distribution. We need more iteration. We need a longer chain to check whether they converge to stationary distribution or not. So we did. We didn't temper transition again, but we run more iterations to match up with the same, almost the same CPU time. So this time, all 10 chains visited 2 modes. And the number of jumps is extremely better than the tempered transition, just because Metropolis is extremely fast, simple algorithm. But we are making about twice more jumps. I mean, RAM is making twice more jumps. And now the relative heights are almost stabilized. So if we spend the same amount of CPU time, Metropolis or RAM produces better MCMC estimate of relative height between these 2 modes. Because when we find multimodal distributions, our concern is how much weight we should put in each mode. So I prepare another example. This target distribution is coming from, do you know equi-energy sampler? Have you ever heard? That is another tempering method developed by Samco. There is, do you know parallel tempering? Okay, but you know Metropolis algorithm, right? Okay, I think that's enough. So the target distribution this time is a mixture of 20 bivariate Gaussian distributions. And depending on the weight and the variance of each Gaussian component, they derive 2 scenarios. The first scenario, each mode is equally weighted with equal variance. And in the second case, if modes are closer to the center, they are more weighted with less variance. And if modes are going farther from the center, the other way around. Let me explain the implementation details, because we don't want to, we just give them some favorable situation. So we run 20 chains, each of length 100,000, and the first 50,000 is burn-in period, discarding the first 50,000 iterations. We don't consider the CPU time because they didn't consider. In our proposal scale, because RAM has a single tuning parameter, the proposal scale, like Metropolis algorithm, we set up these proposal scales in a way that they tuned their own methods. The same way they tuned their methods, we just did that to set up the proposal scales. So everything is following their simulation configurations. So here is a result. So the first row indicates the last 20 iterations of each Markov chain. So it seems like equi-energy sampler visited 20 modes more often than ours. And the ACF, autocorrelation function, decreases faster than ours. But let's think about estimation. Let's think about estimating these 4 moments. For each chain, we can calculate expectation of each coordinate and the squared moment, right? So since we ran 20 chains, we have 20 values of this moment, and 20 values of this moment, and 20 values of these moments. So the estimate is average of these 20 estimate, MCMC estimate. And the number in the parentheses is the standard deviation of these 20 MCMC estimates. And based on these estimates, we calculate the mean squared error. And we also calculate the ratio of mean squared error between our method and each of their method. The ratio is greater than 1, meaning that our RAM performed much better than, not much, it's better than the others in terms of estimation accuracy. Because we got smaller mean squared error. The reason is each chain visited 20 modes more consistently. So the variation between each chain was small compared to theirs. That's why we could get smaller mean squared error. Let's think about the second case. But in this case, we visited 20 modes more often than the others. And the autocorrelation function decreased much faster than the others. And the ratio is quite different. This time, I can say RAM performed much better than the others in terms of estimation accuracy. This also means that our Markov chain visited 20 modes evenly, between chains. So we got smaller variations, smaller standard deviation between 20 estimates. I wouldn't make a strong argument based on these two examples, but at least I can tell you two things. RAM is simple to implement because RAM is a repeated metropolis algorithm. It's just repeating metropolis again and again with a single tuning parameter that is same as metropolis algorithm. So because they share the same proposal scale, it is always possible to replace your metropolis with RAM, even using the same proposal scale. So when you find a multimodal distribution and if you find your metropolis doesn't work well, then replacing your metropolis with RAM doesn't take a lot of effort or time. And also RAM shows much better high-dimensional behavior compared to metropolis algorithm in terms of exploring multimodal distribution. So if you are interested, please visit archive. Let me explain this. We compare the convergence rate in empirical examples, but it is better to compare theoretical rates, convergence rates. But the problem of RAM would be the intractable proposal density function. The Downward proposal density function is actually very complicated. And several people gave us some comments about how we make a downward movement. So Christian Robert, who is the author of famous MCMC book, if you know, he suggested mixing anti-Langevin algorithm plus Langevin algorithm, because that is based on negative derivative and derivative. And Art Owen, professor at Stanford, suggested mixing negative temperature and positive temperature levels in each tempering method. Usually tempering method is the only solution of multimodality in MCMC computation. And I think this downward idea can be used to find a global optimizer, because we know that tempering idea can be used to find a global optimization that is called statistical annealing. And let me conclude this talk by this. Christian Robert gave us a nickname of this algorithm, which is love-hate metropolis algorithm. But the first reaction, we first reacted in this way. Shouldn't it be hate and love? Because we first go down and then go up. And in real situation, if you have a relationship with someone, wouldn't it be better to first hate and then love? Because in this case, it's happy ending, right? Thank you very much. Do you have any questions about time delay estimation or RAM algorithm?
So I had a question about the RAM algorithm, and in particular, if you have some structure in the multimodality. So on slide 12, you have the Gaussian mixture there. Yeah, so that is multimodal in both x1 and x2, those plots. So conditioned on a particular value of x1, you have multi-modality in x2 and vice versa. So if you only had multi-modality kind of along one parameter, is there a way to exploit that in the algorithm to it goes down somehow?
Actually, there are many ways to sample, draw posterior sample, I mean, not posterior, sample from this distribution. One way is to, as you said, alternating each conditional. Like conditioning on this, we sample this, and given this, we sample this. That is kind of Gibbs sampler.
Yeah,
but in your question, the question was, in one direction it is unimodal, but the other is multimodal. Kind of.
That's what I'm wondering if there's, if you assumed that structure. I guess I can think of a couple of problems where I know that structure exists. So then I could use RAM or one of these multimodal methods, but those are, in some ways, your method is more general. So is there a way to speed things up, or would there be a natural proposal distribution?
Maybe we may have to try two cases. Whether it would be faster to sample two-dimensional proposal, or at the same time, or would it be better to conditionally sample each one-dimensional sample? So, we can try both, but my hunch is that conditional will be a little bit slower because that uses some correlated structure in any case, Markov chain. So if Markov chain doesn't got to the stationary distribution, if the correlation doesn't disappear fast, then it takes longer time for the chain to converge to the stationary distribution. So yeah, I haven't tried, but my hunch is that wouldn't it be better to sample two-dimensional sample at the same time instead of using conditional structure alternatively? Maybe not, but I have to try. Yeah. Do you have any questions? So if you find multimodal situation, please try. I would appreciate, really, if you let me know the result.
Thank you.
Thank you.